Section 4.4 and also what comes after it, certainly section 4.6, now the next idea becomes, what if you have a second order equation that has constant coefficients, but it's not homogeneous? And that's what this is about over here, this g of x, where that doesn't have to be zero, right? So for homogeneous, you got a zero on the right side. Now you can have other stuff. That will make the solution a little bit more complex, and you can see it here. The first part of it, the C1y1, C2y2, that looks like the kind of stuff that you'd get from a homogeneous equation, and it is. But then this y sub p, this is the new thing, and most of this section will be about how you can get y sub p. And it depends on what's on the other side of the equation, because different types of functions, like if you have an exponential or if you have a polynomial, it works a little bit differently, but it's the same general idea, and the y sub p tends to look like those. So if you have a polynomial on the right side, then your y sub p is going to be a polynomial. If you have an exponential, your y sub p is going to be an exponential, that kind of thing. So generally, how do you do the solving? First, you get the solution to the corresponding homogeneous equation. So just like the equation you've got, but with a zero on the right side of the equation. So like what we were doing before, like before break. And those we know how to do. We know what to do when we get the two distinct real roots or the repeated roots or the complex roots. And it's basically just going to be those options. It's going to be the exact same as it was before. So that part, it's not new. And that's also the short part. The longer part and the new part is this, finding y sub p. And what's with the subscripts? I guess I should mention that. Y sub c in words is usually called the complementary solution, and y sub p is called the particular solution. So particular in relation to the thing that's on the right side of the equation, essentially. And then if you combine those together, so just add them together, then that's your overall solution. So how do you get y sub p? Well, you have to make an assumption of what its form would look like, and that's based off of what's on the right side of the equation. So what you end up doing, it's down here, where if it's an exponential function, then you would assume that your particular solution is proportional to the same exponential function. So like if it's e to the 5x, then you'd say, okay, well, it's some constant times e to the 5x. So like how there's a big A right here, that big A is supposed to be a constant that then you're going to have to solve for, or a coefficient that you're going to have to solve for. You can have a couple of trig functions, sine and cosine. This is the one that tends to trip people up because of this. If you look over here, you need both pieces, even if what you've got on the right side of your differential equation is just sine or just cosine. You need them both. The reason that you need them both is because of the derivatives. Like how the derivative of sine is cosine, and then the second derivative of sine would be negative sine. But with the derivatives there, you also get a cosine in there. And then the same sort of thing would happen the other way around. If you had a cosine on the right side of the differential equation, you're going to get a sine in there with the first derivative. That's why. It's basically to cover all the bases. So that is the thing that feels a little bit counterintuitive. And that's usually the thing about this that tends to trip people up a little bit. It's if you have sine or cosine, then when you assume the form for y sub p, you need both of them in there. And then if it's a polynomial of the same degree, if there's anything to be careful with there, maybe if the polynomial has powers of x that are missing, something like that. Like what if the right side of your equation was x squared plus 3? So then there's no x term. Then what you'd end up with would be maybe something like ax squared plus bx plus c for the form of y sub p. So you'd still need to include that. And that's, again, because of the derivatives, because then you might have an x term in there. And then this thing with the bracket over here, none of those functions have restrictions on the domain. That's more or less a reference to the trig functions, because I think that's a logical question. Why is it just sine and cosine? Why not the other trig functions? Well, the other trig functions have discontinuities where they're undefined, right? And so that's basically the reason. And then if you look at the other types of things that are in here, they're continuous everywhere. Polynomials, exponential functions. So I guess you could also say, well, that maybe that's why it's an exponential function, but no natural log, because there are values where natural log is undefined, right? If you have a non-positive number. So it's just those where undetermined coefficients will work. There are other methods for other types of functions. 4.6 is variation of parameters, and that covers some different stuff. And so we'll get there when we get there. But for now, it's just this stuff. Down here, let's see. These are kind of some extra things that will come up if your function on the right side of the equation is a product of some of the above forms. You make the same kinds of assumptions. Sometimes you can reduce the number of arbitrary constants that you have to solve for, which is kind of nice. But that just means, like, what if you have, x sine x? Then you would have ax plus b times c sine x plus d cosine x, all in parentheses, kind of like that. So you would have to involve both forms. If you have a sum of the above forms, you can break that up into pieces and just do individual pieces of the sum and then kind of combine them all together at the end where you'd have multiple y sub p's. It seems like that would be more work, but that work ends up being a lot less difficult if you do it like that. So if you do end up with a sum of terms, go through and get them one by one and then combine it back together at the end. There will be an example in here where we do it. If you don't do it that way, it's really, really long. It's long to begin with, but it's really long otherwise. Let's see, then this last part is kind of like what you do with a repeated root, where if you get a particular solution that already showed up in the complementary solution, you'd have to add in the smallest power of x multiplied by that particular solution to where it's distinct, where it's not something that's part of the complementary solution. So that part, it works just like the way repeated root works. Okay, now we can actually get to the examples. So for the first one, this one's not too bad if we want to get the general solution of y double prime plus 2y prime minus 3y equals 2e to the 3x. So here's the first part, the homogeneous analog. So you just replace that 2e to the 3x on the right with a 0. And then this is a thing that we already know how to solve, where we say, okay, we can get the auxiliary equation, right? We get the lambdas in there. And then this is one that factors, and it looks like lambda could be either -3 or 1. So then that's what we get for our complementary solution. c1 e to the -3x plus c2 e to the x. Then here's the new part, the particular solution. So what we're going to assume, I kind of want this still visible up here, because of the 2e to the 3x, we say, okay, it should be e to the same power, but maybe with a different coefficient. So a is the coefficient that we're going to solve for. So it's the undetermined coefficient right now. And this is part here that's in red. This is just kind of the logic behind it. If the differential equation has a term containing e to the 3x on the right side, then y has to have an e to the 3x in it. Otherwise, you'd never be able to get that on the right side. So, okay, sure, that would have to be true. But I just wanted to kind of interject that in there. But then we say, well, if y sub p is a e to the 3x, then the first and second derivatives are right here, which aren't too bad. Basically, it's just pulling the exponent down. And then if you sub into the differential equation, so subbing into this up here, then you're going to put 9a e to the 3x there, and then 3a e to the 3x there, and then an a e to the 3x there. All right, so if I go down, there's y sub p double prime, there's y sub p prime, there's y sub p. And then it looks like we can basically just combine everything on the left, right? And say, well, 9 plus 6 minus 3 is 12. So 12a e to the 3x is equal to 2e to the 3x. So 12a is equal to 2. And sorry, I messed up there and had to scratch some stuff out. But then a would have to be 1/6. Okay? Well, that solves for the coefficient. So then the particular solution, y sub p, is going to be 1/6 e to the 3x right there. So then, to get the general solution, you just add the complementary and particular solutions together. So here's our complementary solution, and then down here is the particular solution, and that's it. And that takes care of that one. All right, with number 2, notice this is one where we've got a trig function over here. And this is the one where I said you have to be careful. So we won't see that right away, but we're going to see it soon enough. So the first thing, getting the complementary solution. So just use the corresponding homogeneous equation, get that 0 on the right. And then there's the auxiliary equation. That factors really easily. And so either lambda equals 0 or lambda equals -2. And then there's the complementary solution. So I guess C1 e to the 0t plus C2 e to the -2t. But the e to the 0 is just going to be 1. So C1 plus C2 e to the -2t. Okay, that part's not so bad. Then down here, this is the step where you got to be careful right here, where the form of the particular solution, it's got to include sine 2t and cosine 2t because of the first derivative. So undetermined coefficient a times sine 2t plus undetermined coefficient b times cosine 2t. And then the original differential equation up toward the top, second order, we're going to need the first and second derivatives. So there they are. And then when you substitute in, so okay, there's the second derivative, then plus 2 times the first derivative, and then that's going to be equal to 4 sine 2t. Here on the left side, basically I just kind of rearranged stuff so I could combine like terms easier. I put the sine 2t stuff together and the cosine 2t stuff together. That's basically what this line is. And then I said, okay, well, if those things have to match up, then the coefficient of sine 2t on the left, it's got to be equal to 4. And the coefficient of cosine 2t has got to be 0 because there's no cosine 2t over here on the right side. Okay, well then we've got a system of two equations with two unknowns. And basically I just added these two together. And then -8b is equal to 4. So that means b is -1/2. But then if you back substitute into either one of these up here, I picked the second one, then you'd get 4a plus 2 equals 0. So a is also -1/2. So that means that y sub p is this, -1/2 sine 2t minus 1/2 cosine 2t. And then just like before, you get the general solution by adding the complementary and particular solutions together. All right, so there's the general solution. There's also an IVP. Let me scroll back up for a second. Y of 0 equals -3/2. Y prime of 0 equals 7. All right, so if we go back down here, we should be able to solve for C1 and C2. So, okay, well then we've got that if we substitute in a 0, then sine 2t is 0, cosine 2t is going to be 1. So that's how I have that -1/2. It's like, all right, well, if you subbed in 0 for t, that's what you're going to end up with. And that's why C2 is just here by itself, because it's going to be C2 times 1, right, times e to the 0. So if -3/2 is C1 plus C2 minus 1/2, which we can then rewrite a little bit to make it look a little simpler, as C1 plus C2 equals -1. And then here I just took the first derivative of this thing up here and then substitute it in. And eventually what you end up with is that 8 is -2c2. So C2 is -4. And then using this over here and substituting in, C1's got to be 3. So then what you end up with for the solution to the IVP, C1's 3, C2's -4. And so there's that solution. Next, we've got one with a polynomial on the right side. If there's anything to watch out for here, it's that the polynomial has a missing term. It doesn't have an x term. But when we write out the form of the particular solution, that's got to be in there because of the first derivative. So we're only looking for the particular solution this time. I had kind of set this one up this way in order to save time in class, basically. But the homogeneous analog here couldn't possibly have an x squared in it, right? It's going to have e being raised to powers, not x being raised to powers. So you wouldn't have to find y complement first to see if there was repetition with the particular solution compared to the complementary solution. There's no way that's going to happen. So you can jump right to the particular solution, and this right here is the key step. that the form should be ax squared plus bx plus c. So I know I'm kind of harping on this, but that bx part, that's so easy to forget about. I've certainly done it before. But that's got to be in there just in the general form of y sub p, even though there's no x term up here. And the derivatives, at least since this is a polynomial, they're super simple, right? Just some power rules. And then if we substitute into the differential equation, let's see. So if we go ahead and do that, then there's the second derivative, there's the first derivative, and then there's y sub p. And then if you combine like terms, which is eventually what I end up doing, I guess on about this line here. So 3ax squared plus this multiplied by x, and then plus this here for the constant. So then you say, all right, well then 3a must be equal to negative 3. So a is negative 1. And then negative 6a plus 3b has to be 0 because there's no x term over here. But then since we already know what a is, since we know it's a negative 1, we can sub that in. Then we can solve for b, get that's negative 2. And then this thing right here, the 4a minus 3b plus 3c, that's got to be equal to 14. So then we already know what a and b are. We can sub in for those. We eventually get that c is 4. So then there's the particular solution. So negative x squared minus 2x plus 4. So the polynomial ones tend not to be too bad, I guess, unless the degree of the polynomial is really high. Right? If this was a 5th degree polynomial, this would obviously be a lot worse. But, you know, when it's just a quadratic, not too bad. This one is epic. And it's because there's all kinds of stuff happening on the right side. I had to do this somewhere. I had to get this stuff in. But this is one that's really, really long. But look at what's going on up here. We've got two terms, right? We've got the trig function here, but then we have this other term, which is actually two types multiplied together. So the x times e to the x, that's technically a polynomial multiplied by an exponential, right? Because the x, it's a pretty simple polynomial, but it's a polynomial. And then the e to the x, that's definitely an exponential. So there's a lot of stuff to do here. We'll get the complementary solution first. That part's not going to be anything different. You say, okay, well, what if there was a 0 on the right side and it was homogeneous, and then we just solve that? Well, it looks like here we got the difference of squares, so we end up with that lambda is 2 or lambda is negative 2. So y complement, right? Not too crazy. To get the particular solution, this one is much easier if it's done in separate pieces. If you try to do that whole right side all at once, it's doable, but it's really long. And that's really long in a relative sense compared to this thing that's 2 pages long. So I guess that's what I like. It's long, all right? So we're just not going to go down that road. We're going to do them separately. So since we have that sum up here, we can say, well, down here, first we'll solve this, where we just have x e to the x on the right. Then we'll solve it this way with the cosine of 2x on the right. And then we'll end up with two particular solutions. So like a y sub p1 and a y sub p2. And then we just add them together at the very end. All right, so first, what if we have x e to the x? Notice what happens in this line where I say, okay, well, this part's a polynomial, the x. So you would have to have it as ax plus b, right, to get all the powers in there. And also, I guess, really to control for what happens with the first derivative. So there's the part that's for the polynomial, and then undetermined coefficient times e to the x. But then if you distributed, you could write it this way, where there are less arbitrary constants or arbitrary coefficients. And that's really all I'm doing here. And I know I'm recycling and using the a and b, and they mean something slightly different than they did here, right? I guess that it would be a times c over here is a over here, and then b times c over here is b on this one that's toward the right. But this way here has less arbitrary constants, and that equals a little bit less work. That's why we're going that route. This is 2 pages long as it is. If we can cut out work, we're cutting out work. Okay, so now I multiplied this out because I thought it would make the derivatives easier. And then I went ahead and took them. So first derivative, second derivative, you got a product rule in there that you got to deal with. But other than that, I don't think they're too bad. And then I suppose combine like terms where you can combine like terms because that's going to make the solving easier in the long run. Then if we substitute in, then there's the second derivative, and then it looks like there's the original function. So from there, we can simplify things a little bit, it looks like. So I simplified what I could here, and then say, okay, well then we just have x e to the x here. We don't have just an e to the x term, right? So then you can say, okay, well then negative 3a must be 1, which means that a has to be negative 1/3. But then 2a minus 3b has to be equal to 0 because there's no e to the x term on the right. So we already know what a is. That's negative 1/3. We can sub that in, and then we can eventually solve for b, which is negative 2/9. So then there's the first particular solution right there. And I guess up here, right in this line right here, I should say equals x e to the x. It looks like I'm being a little bit sloppy there. I missed one piece writing this out. So sorry about that. That should be in here. Let's see. Then going down here to where we had the other part with the cosine 2x. And then remember, when you get the general form of the particular solution, you would need sine 2x and cosine 2x in there. So there it is, a sine 2x plus b cosine 2x. We get the first and second derivatives. And then if we substitute in, there's the second derivative, and then there's y sub p2. And then if we combine like terms, we end up here. But then since there's no sine 2x on the right side, then a has to be 0. And then since the coefficient on the right side is just a 1, it looks like b has to be negative 1/8. So y sub p2, negative 1/8 cosine 2x. And then the solution, basically you just combine everything together. So this was from the very beginning, y sub c, it's these first two terms. Then the next two terms, the negative 1/3 x e to the x minus 2/9 e to the x, that's y sub p1, the part from when we had just x e to the x on the right side. And then the minus 1/8 cosine 2x, that's from right up here. So that one's long. This does occasionally happen, so I did have to put one of these in here where it was kind of epic in length. One last one, and you know what this is going to have to be. The one thing that hasn't come up yet, which is what happens when the particular solution repeats something that's already in the complementary solution. So with this one, as usual, start with the homogeneous analog, get the complementary solution first. This doesn't look too bad, and it's not. You end up with the complementary solution is c1 e to the negative 3t plus c2 e to the 2t. All right, well then you can see what's coming here because what's on the right side, 5e to the 2t, it seems like that's something you could get right here with a certain arbitrary value for c2. But we'll see how this all shakes out. So c2 e to the 2t is part of that. So then what we're going to have to do is assume that the particular solution is of the form at e to the 2t. So there it is. There's that extra t in there as a factor. And so that way that would differentiate it from what's in the complementary solution. So the way that you handle this, just like what you do with a repeated root that we've had before. So then you say, all right, well then if that's what y sub p is, if that's our particular solution, then if we're going to get the derivatives, there's going to be a product rule in there. And I guess combine like terms where you can combine like terms. So ultimately what you end up with is that for the second derivative and then that for the first. And if we substitute in, so there's everything substituted in, and then if you combine like terms, you say, oh, well, 5a e to the 2t is equal to 5 e to the 2t. That looks like it's pretty easy to solve. A has to be 1. So then y sub p is just t e to the 2t, and there's the general solution. So there's kind of the complementary solution, those first two terms. There's the particular solution in the last term. So there's that situation where if the the particular solution is going to end up being something that's already been covered by the complementary solution. You just have to add in the independent variable again as a factor of the particular solution. Or I guess however many times you need it so that it's not part of the complementary solution anymore.